The sky over Hunan province does not just darken. It ceases to exist. It is August 1975. The air is heavy. Not merely with moisture, but with a palpable, crushing weight. An atmospheric collision is taking place above central China. Typhoon Nina, a swirling vortex of thermodynamic violence, has traveled thousands of kilometers from the warm waters of the Pacific. It has been blocked by a cold front, stalled in the heavens, like a cog jammed in a machine. The result is not rain. It is a deluge that defies the historical memory of the region. Imagine the sound. It is a roar that drowns out thought. On the ground, the soil has long since surrendered. The clay and silt, usually thirsty and cracking under the summer sun, have reached total saturation. Every pore in the earth is filled. The water table rises to meet the surface, turning solid ground into a liquefied trap. And in the center of this sodden landscape stands the Banqiao Dam. They call it the Iron Dam. It was built to be indestructible, a triumph of human will over the unruly forces of nature. Engineers calculated the risks. They looked at the history of flooding. They ran the numbers. And they built a structure designed to withstand a 1 in 1,000 year flood. But the atmosphere does not care for human statistics. The storm dumping water onto the Huai River basin is not a 1 in 1,000 year event. It is a 1 in 2,000 year anomaly. Deep inside the reservoir, the physics of disaster are accumulating, molecule by molecule. Consider the hydrostatic pressure. Pressure is defined as the force exerted per unit area in a fluid at rest. This pressure increases linearly with depth. The formula is simple. Density times gravity times height. But as the rain falls 1,060 millimeters in just 24 hours, more than the region typically receives in a full year, that variable of height is skyrocketing. With every centimeter the water rises, the potential energy stored behind the earthen wall grows exponentially. This is not just water. It is mass waiting to become motion. Hundreds of millions of cubic meters of liquid are pressing against the clay core of the dam. The water seeks a weakness. It pushes into microscopic fissures in the compacted soil. It probes the intake valves. It weighs heavily against the steel sluice gates. Inside the control room, the air is thick with panic and cigarette smoke. The operators are blind. The storm has severed communication lines. The telegraph wires are down. They are isolated in a roaring void. They try to open the sluice gates to relieve the pressure, to bleed off some of this terrifying potential energy. But the mechanics of the river fight back. Years of sedimentation have built up against the base of the dam. The heavy silt, dragged along the riverbed by friction and gravity, has clogged the gates. They are jammed. The relief valves are choked. The reservoir is a sealed pressure cooker. And the heat is rising. The water level creeps past the safe line. It swallows the flood markers. It reaches 117 meters above sea level. Then 118. The physics of buoyancy and displacement are now working against the structure. As the water rises, it begins to saturate the dam itself from the inside out. The sheer strength of the soil, the internal friction that holds the particles of clay and sand together, begins to degrade. This is known as pore water pressure. As water forces its way between the soil particles, it pushes them apart. reducing the contact forces that give the earth its solidity. The dam is losing its internal cohesion. It is turning from a solid barrier into a semi-solid slurry. The moment of failure begins at the crest. The water line breaches the top of the dam. This is the phenomenon of overtopping. In concrete dams, overtopping is dangerous. In earthen dams, it is a death sentence. As the water spills over the top, it possesses kinetic energy. It flows down the dry, downstream face of the dam. It is no longer static. It is a scouring agent. The water acts like a rasp. It strips away the grass. It eats into the topsoil. It finds a groove and digs in. This creates a channel. As the channel deepens, the velocity of the water increases. According to Bernoulli's principle, as the velocity of a fluid increases, its pressure decreases. But the erosive power, the shear stress exerted on the boundary, magnifies. The water cuts a V-shaped gash into the face of the dam. The earth crumbles. Chunks of clay, the size of cars, are undercut and collapse into the rushing stream, instantly dissolved into mud. The breach widens. The structural integrity of the crest is compromised. The iron dam is bleeding. Most channels stop at the surface. But here at Surphysia, we dive into the math that governs reality. If you want to survive the next catastrophe with science, make sure you are subscribed and the notification bell is active. Now, we witness the terminal escalation. It is 1 a.m. On August 8th. The storm is howling. But a new sound emerges. A deep, resonant cracking that vibrates through the bedrock. The breach in the dam reaches a critical threshold. The remaining structure can no longer support the immense load of the water behind it. The forces of tension and shear overcome the material strength of the dam. It does not fall. It disintegrates. In a matter of seconds, the potential energy of 600 million cubic meters of water is converted into kinetic energy. The dam wall vanishes. A vertical wall of water, 6 meters high and 12 kilometers wide, explodes outward. This is not a flood. It is a shockwave. The water accelerates to 50 kilometers per hour. It moves with the momentum of a freight train that spans the horizon. The physics of this wave are terrifying. It is a hydraulic bore, a phenomenon where a moving wave front creates a sudden increase in depth. The wave front is turbulent, a churning grinder of mud, debris, and raw force. Consider the impact on a single village in the valley below. A house stands in the dark. The occupants hear a rumble, like an approaching earthquake. The wave arrives. The force exerted by the water is proportional to the square of its velocity. At 50 kilometers per hour, water acts less like a liquid and more like a solid battering ram. The wavefront hits the brick walls of the house. The masonry does not have time to crumble. It is pulverized. The mortar bonds shatter instantly. Under the impact pressure, the roof collapses as the supporting walls are swept away. In milliseconds, the air inside the house is compressed violently before being displaced by the liquid, blowing out windows before the water even touches them. The river dragon, as the locals would later call it, rampages down the valley. But the horror is compounded by the domino effect. The Banqiao Dam was the highest in a chain. As this massive volume of water rushes downstream, it slams into the next dam, and the next. The Shimantan Dam, the Jugo Dam. They are subjected to a sudden, catastrophic increase in load. that no engineer could have designed for. They are not overtopped gradually. They are smashed. One by one. 62 dams fail in sequence. The volume of the flood multiplies. The kinetic energy accumulates. The water scours the land. Down to the bedrock. It strips away topsoil. That has been there for 10,000 years. It twists steel railway tracks into corkscrews. This is plastic deformation. On a massive scale. The yield strength of the steel, millions of pascals, is exceeded by the relentless momentum of the water. And the debris it carries, trees, boulders, and buildings, become projectiles within the flow, adding to the destructive mass. The thermodynamics of the aftermath are equally grim. The floodwaters settle over an area of thousands of square kilometers. The sun returns. The stagnant water begins to heat up. It becomes a breeding ground for bacteria. The biological decay begins. But let us return to the engineering failure. For that is where the lesson lies. Why did the Iron Dam fail? It was not just the rain. It was a failure of prediction. And a failure of maintenance. The hydrologists of the 1950s used limited data sets. They assumed a linear progression of weather patterns. They did not account for the extreme outliers. The black swan events that chaos theory tells us are inevitable. They built for a standard deviation, not for the edge of the bell curve. Furthermore, the mechanism of the sluice gates reveals a critical oversight in fluid dynamics management. The engineers underestimated the coefficient of friction and the settling velocity of the silt in the Huai River. They viewed the water as a pure fluid in their calculations, neglecting the multiphase nature of river water, which carries suspended solids. Over years, these solids precipitated out of the flow, creating a concrete-like barrier at the base of the gates. When the emergency came, the mechanical advantage of the winches was insufficient to overcome the resistance of the silt. The safety mechanism was paralyzed by the very environment it was meant to control. Survivability in such a scenario is a matter of understanding elevation and potential energy. When the warning signs appear, the relentless rain, the saturated soil, the only engineering solution for the individual is distance and height. One must calculate the path of least resistance for the fluid and ensure one is not in it. The villagers who understood the topography, who moved to the highest ridgelines immediately, survived. Those who relied on the structural integrity of the dam, who trusted the iron name, perished. The Banqiao disaster teaches us that the factor of safety is never high enough when dealing with complex, chaotic systems like the atmosphere. We build static structures in a dynamic world. We use linear mathematics to contain non-linear forces. The concrete and the clay are strong, but they are finite. The energy of the storm is, for all practical purposes, infinite. When the two collide, the physics of failure are the only law that remains. The atomic lattice of the steel stretches. The ionic bonds of the clay dissolve. The potential becomes kinetic. And the silence of the aftermath is the only sound that is louder than the roar of the collapse. The universe is full of chaos, but we are here to decode it. For more deep dives into the physics of survival, stay connected to Surphysia.